All right, top of the morning, Algebraites. On this great day, we're going to be factoring polynomials. Factoring polynomials. This is absolutely essential, and I've said that already for a couple other things. But why is this essential? Because we are now undoing, we're going to undo what we just did in the warm-up here. So as we see with this warm-up, I can send in the -5 to both of those, and we get -5x plus 10. So the question is, if I multiply to get here, how do I get back? We already do that. If I had some number, I have 10, and you add 2 to it. That gives me 12. So how do I get back to 10? Oh, I have to subtract 2. Because these guys here are called inverses. So when we do the inverse, we can undo it. I can tie my shoe, I can untie my shoe. I can open the door, I can close the door. So we can inverse things, we can undo. So how do I undo the distributive property? And technically you're not, you're using the distributive property just the other way. We call it factoring. We go backwards. Now this is extremely important for this reason. You don't have to write any of this down, I'm just going to talk real quick. If I gave you an equation, 3x plus 7 equals 2, you guys already know how to solve this. Oh, I know what to do, Swenson. We can subtract 7 from both sides like this, and we get 3x equals -5. Oh, and then I'm going to divide 3 on both sides, and we're done. And we have my answer. X equals -5/3. But what if I messed it up a little bit? What if I said this, 3x squared plus 2x plus 7 is 2? And I say for you to solve it. You say, oh, I'll just do the same thing. I'll subtract 7 from both sides. Good, no problem. 3x squared plus 2x equals -7. Divide? Well, because I need to get x by itself. But I don't want to subtract 2x because now x is on this side and on this side. Really? So what do I do? And the answer is you don't have the skills yet to accomplish this without graphing or guessing and checking or something like that. So what we're going to do is figure out how to get a problem like this and convert it to a problem like this, because we already know how to solve these ones. We just keep doing the inverses. Subtract here, divide here, we're done. Okay? So the skills that we're learning today are going to lay that foundation so that we can convert this to something like this and then solve. And here are the answers for the B and C. So of course, like we just mentioned, how do we undo this? Because oftentimes we're going to need to undo. So today we're going to focus on undoing just what we did for warm-up. So 2 terms that we need, first off, is called factor of a number. What is the factor of a number? The factor of a number. Well, let's think about it. If I told you 12, what would you say? What are some factors of 12? Just shout it out. Anything.
24.
Okay, factors.
6.
6 and 2. 3 and
4.
12 and
1.
Good. Why? Because these 2 whole numbers or integers multiply to get that number up there. Did any of you say, oh, 4.5 and some other point something? Well, no. Because when we think factors, we don't think fractions and decimals. We think all integers, all whole numbers. In this case, we're not dealing with negatives. All right, so factors of A. Factors of A. Any number that evenly divides A. So we are going to expand that. Just point that out, that it doesn't have to only be numbers. In fact, it could be any expression that evenly divides. Right now, we're going to start with numbers, and we'll show you that it goes to A's, and later it can be some other thing like A minus 2 or something. All right. Next is a phrase, GCF. We will come across a gazillion times today and Monday, and that simply means greatest common factor. Greatest common factor. Let's actually do an example right here while we're thinking about it. Greatest common factor. If I gave you 2 numbers, 24 and 30. Talk real quick. What is a common factor, or the greatest common factor between the two of these? Go. So one thing we could do is, some of you in your head, you thought about this, and you can make a tree diagram. A lot of us said 4 times 6, and then over here we said 6 times 5, and we did notice, oh look, there's the 6 and the 5. That does work, but we're going to show you how to make this work always. So I am going to show you today 2 methods. One is called the tree method, like this, also called prime factorization. And another method is called the ladder method, something you've probably not seen, but is one of my more favorite methods because it's very flexible. It does a lot of different things. All right, so it doesn't always have to be pure numbers. We could also be looking for GCF of anything, any monomials. In this case, I have a quadratic monomial. Here, I just have a constant. So let's do the tree method for these. First, we have a 15x squared, and over here we have an 18. What you're going to do is just start factoring however you can factor. Any number or letters that you can pull out that you can divide by, right? So 15. I can do 15 and, I can do 3 and 5. And notice the x can actually break up too. In fact, I'll just go ahead and put the x squared on one of them. Because 3 times 15x squared, 3 times 5x squared is 15x squared. Now I'm going to keep breaking up. This guy here breaks up to a 5 and an x squared, and the x breaks up to an x and an x. Notice what's happening here. Everything is multiplication. It's all multiply. Now, the 3 does not break down further in terms of integers. We can do 3 and a 1, but that's pointless because I can always do 3 and a 1, 3 and a 1, 3 and a 1, and I would never stop. So notice here are my factors, and I'll just write it out so that you can see it. This becomes 3 times 5 times x times x. Those are all my factors, and that's called prime factorization. We're going to do the same thing with 18, and give me some factors. Anybody? Go ahead. 9 and 2. So I break up the 9 and the 2. 2 can stop because 2 is prime. So the 9 is 3 times 3. Again, in our head, we can just think there's multiply. You don't have to draw that dot every single time. And my prime factorization of this is 3 times 3 times 2. I'm not going to put the square right now, although that is part of it. It's actually 3 squared, but we'll leave it like this. In order to find the GCF, all you have to do is find the common things. That's it. I have a 3 here, a 3 here, and nothing else. There is no other. A 5 here, but no 5 here. Another 3 here, but not another 3 here. I have x's here, but no x's there. So, in the end, my GCF is just 3. Let me show you a different method here that to me is a little bit more clean, because here you have to break up, you have 2 sections, you break it up into all these branches. But here I'm just going to go set them side by side. So put the 15x squared here, a little bit of a space, put 18 next to it. And I'm going to put this box, a half box, around it, underneath like this. What I'm going to pull out on the outside is any factor, and down below I'm just going to divide. So that's going to be called my quotient. So think about this. I just have to look at the numbers and or letters and think, what is one common factor? It doesn't have to be the greatest, just anything. Oh, 15 and 8. Oh, both of them can be divided by 3. So put the 3 on the outside. Now you take this 15x squared and divide that by 3. So we get down below, we get 5x squared. Now we take the 18, divide that by 3, and we get a 6 down below. And now I ask myself that same question. Is there anything else I can factor out of these two? And the answer is, well, just a 1. That's it. When your last thing over here is a 1, then you're done. In a moment, it will see it extended beyond just one level, because we can keep going with the levels. Now, whatever we get over here, the product is the GCF. So in this case, it's just 3. Because 3 is not multiplying with anything else. I didn't pull anything else out of those two. Your turn. Please do both methods using the 24a cubed and the 36. Tree over here, ladder over there. Take a few moments and go. So if I do a tree diagram on this, the 24 is 12 and 2 probably. And then the 12 can go 2 and 6, and then another 2 and a 3. And notice that the a cubed is actually very simple. The a cubed is just a times a times a. A times a times a. You don't have to break it up into 2. I broke this one up into 3 just because it's straightforward. A times a times a. So that means the prime factorization is 2 times 2 times 2 times 3 times a times a times a. I didn't leave myself enough room there, so let me fix that. Now the 36 breaks up 12 and 3, 3 and 4, 2 and 2. So the prime factorization here is 2 times 2 times 3 times 3, and did I mess up? And that's it. Okay, so now we start looking through what's common. I have a 2 here. I have another 2 there. And let's see, we have a 3 here and a 3 here. So the GCF, the GCF is 2 times 2 times 3. And this is really sloppy. I do apologize for that. Let me clean that up here. So the answer is 12. The GCF is 12. And notice that 12 divides this, gives me a 2. 12 divides this and gives me a 3. In fact, my first level, see the 12 times 2 and the 12 times 3? That actually shows me, oh, I could have stopped right there had I enough foresight. Now, I like this next method because it's a little bit more compact. So let's go ahead and write the two numbers out, 24a cubed. And the nice thing about this is that I'm not doing prime factorization. Just what is any number that divides both of these numbers here, the monomials? Well, I'm going to start small. We already know the answer is 12, but I'm going to start small. Let's just do 2. So divide by 2 to get 12a cubed. Divide by 2 to get 18. Oh, I see a 6 in both of those, right? So let's put a 6 outside. Now divide by 6, I get a 2a cubed. And here I divide by 6, and I get a 3. Since there is no other common factor here besides a 1, these together are my GCF. The GCF is 2 times 6, which is 12. And notice I'm multiplying, always multiplying here. Now we're getting crazier. We're going to do the same idea, and some of you are going to realize that the tree method is very tedious, especially when we get to numbers like this. The ladder method you might find to be better. And in the end, I don't care if you do neither one of these. If you can see it, just looking at it, if you can just see the answer, then just write the answer. Okay? I'm not saying I see the answer in the back of my book. That's not what I'm saying. I'm saying I see the answer because it comes to me. All right, so let's see here. So I'm going to write these both down. Again, it's going to get tedious. In fact, what's nice is I'm going to forget about the x's and the y's in a second because I can just write those out pretty easily. Okay? So let's do 30. 10 and 3, and then 2 and 5. So looking just at the bottom there, we have 2 times 3 times 5, and I'm going to bring down those up here. See, I see the x squared. So I'm just going to bring that down as an x times x. And then I'm going to bring down the y cubed as a y times y times y. 18. Same thing. 6. That's not a 6. 3 times 3 gives me 9. Remember, we're doing multiplication, not adding. Now, if I write this one out, it's a 3 times a 3 times a 2 times an x, 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 y, y. And that came from up there. Let's start circling the things that are the same. Here's a 2, here's a 2. There's a 3, there's a 3. Let's see, x's, I have an x there, x there, x there, x there. Ran out of x's that are the same. And a pair of y's there, a pair of y's there. Okay? Now what we need to do is since they're circled, it doesn't matter which one we look at. We're just looking at one of them, one of the circles. I'll just look at that one there. And I'm going to write it out as the GCF equals 3 times 2 times x times x times y times y. 6x squared y squared. Granted, I completely agree with you. It's a little bit tedious. But for those of us who are practicing, this method works out fine. It just explodes everything out. You see all the parts, and you start comparing the parts. All right, but for those of us who don't see it mentally, we're going to keep showing you another method here. This method I really like, and I leave some space there, and I'm just going to find out some things that are common between them. Okay? I'm going to pretend I don't see the 6, just so that I can break it up further, although most likely in real life you see the 6. So I'm going to put a 2 here, but notice I'll put a 2x. Because I see x's in both of them, I see a 2 in both of them. So I get 15 here, x, y cubed, 9x squared, y squared. Now I find out something else here that can divide everything. Maybe, I do notice another x, I notice another y, I notice another 3, in fact. So I'll do a 3x and a y out there. I'm doing it more complicated than you need to, folks. Again, whatever you see, pull it out. See it in a different way than I do? That's word up. All right, 5, the x's go away. I'm left with the y squared. This is a 3. I have 1 x left and 1 y left. Oh, I forgot about that y, so I'll pull that one out now. There's another y. Lastly, I get 5y and 3x. Oh, there are no common factors between these two besides a 1. So there is a phrase for that. That's called relatively prime. Compared to each other, they're prime. So my answer here is just the product here. 2 times 3 is 6. Then x times x times x is x squared. And then I have a y here times that y there, y squared. Same answer, different method. Again, whatever cranks your tractor, whatever floats your boat. Or if neither one of those are good for you and you still got the answer without doing this, do that too. Let's look at this again, as it does get a little bit tedious. I'm only going to do the 45 and the 18 right now. Now, some of you quickly see, look, a 9 and a 5 and a 9 and a 2. Because the 2 and the 5 can't go any further, we can actually stop there. So you don't have to go all the way to prime factorization. You can, but there we go. And notice in terms of this guy here, the a, that's a times a times a times a, which is tedious. Or you could have just said, oh, look, that has an a cubed, which means the a cubed is shared in both of them. So now I'm pulling the 9 out. So let me do GCF down here. GCF is equal to the 9. Now I'm saying the a cubed, because this one has a times a times a times b times b. And then we notice that 3 a's are in common there, and 1 b is in common there, and we get this. So I'll do the same thing over here. This time I'll keep the letters in like I did before, but I will choose larger numbers and letters than I did before. So 18a cubed and a b squared. Box it there. I can pull a 9 out from there, so I get a 5a4, and I forgot something there, b, and then 2a cubed b squared. Now, if I just look at just the b's, oh, well, the common thing, there's a 1b there, 2 b's there, so I can just pull out 1b, and that's it. A b here. So now we get 5a4, no more b, 2a square cube, and 1 more b there. And if we do it again, I'll pull out the a's this time. a3. So this gives me 5a, and this one gives me 2b. Because 5a and 2b have no common factors, my GCF is just going to be the product there. 9a cubed b, just like we got there. Now, don't circle that like I did, because that's not the answer. The answer is the 9a cubed b. That's the answer. Over here, I was just showing you that where the answer comes from. The point of finding the GCF actually brings us to this. What we want to be able to do is to undo what we did on page 1. Undo what we did. How can I rewrite this thing right here, but as a distributive property? So in the end, I end up with something like this, with a number plus a number and a number here, right? I want to break it up. I want to factor it. Because when I do the distributive property, that happens and gives me that. So how do I go backwards there? Okay. The key thing here is so that you know what the definition is. Anytime you hear the word factor or phrase factor out, what that means is turn into a multiplication problem. What you're trying to do is if I have the number 24 and you want to factor it, that's 12 times 2. So you turn 24 into a product, 12 times 2. So that's what we're doing. Because right now, in example C, that's a sum. I have 2x squared plus a 4x. So how do I make this into a product? Something times something else. Something times something else. So I need to ask myself, what is the GCF of these two here? Now, however, whatever method works for you, if you want to do the ladder method, that's great. If you just jump to the answer, that's great. Or if you want to do prime factorization. Notice I'm actually going to do, just show you that you can do the ladder method just right here. So I see a 2 that comes out. So I get x squared plus 2x. What letter do we see that's common? See one of the x's. So those drop down to be a 2. So here, my answer is on the outside. Look, the answer is on the outside. So these two right here, 2x, that's the common factor. 2x. And this part stays inside. So 2x times x plus 2. 2x times x plus 2. So just to check this one, if you would like to do the long method, or not the long method, but a longer method, you just start pulling out factors. I see a 3 that can come out here. So I get 3a cubed minus 5a squared. And then I notice an a. Now I'm taking the long way. Some of you said, oh, I can do faster than that, Swenson. Great, then do faster than I just did. And I can pull out another a. 3a minus a 5. So this guy is what's left inside the parentheses, 3a minus 5. And all of these product multiplied is the GCF that's outside. So we know we're right because if I distribute this in, 3a squared times 3a, 3 times 3 is 9, a squared times a is a cubed. 3a squared times negative 5 is negative 15a squared. So distributing that back out gets you back where you started. Now, lest you thought we were going to stop there, now what we're going to do is pull out even more from more. More from more. Crazy here. So, same idea, but I'm looking at a trinomial instead of a binomial. So the question is, what number, letter, or even a negative can be pulled out from everything? Well, I'm going to pull out a negative. Well, you don't have to do the negative, but I think it's very common. It's very common to, if there's a negative there, to factor the negative out. Factor out that negative. That's in the front. It's a very common thing. So I'll encourage you to do that, but officially you don't really have to. So I'll pull out the negative, and let's see what else. A 12, an 18, and a 20. You know, the only thing I can think of is a 3, so I'm just going to start with a 3, okay? So divide everything. I get a positive 4x cubed. I get a negative 6x squared. And here I get a negative, excuse me, positive now, 9x. So look at the 4, the 6, and the 9. There are no common factors between the 4, the 6, and the 9. So I'm done with that part. Notice the letters. So what can we pull out here? I can pull out an x, so let's go ahead and do that. So pull out an x here from each one of them. So this is 4x squared. This here gives me a 6 and an x, and this one here is left with a 9. The x goes away. And notice there is no common factor in all of these, so this component right here, this guy is one group, and this guy, the monomial, is the one that's outside. So negative 3x times 4x squared minus 6x plus 9. So as I mentioned, it's very common if the leading coefficient here has a negative, it's very common to pull it out here so that this guy here is positive. Notice negative, positive, negative is now positive, negative, positive. So everything's oppositified on the inside. All right, go ahead and pause, try those two, and then check the answer in a second. And here are your results. The last thing we're going to work on in this lesson is we're going to be finding dimensions. So sometimes we're going to see problems that look like this. Notice in the problems that we've done before, we were looking for the area because we had the dimensions and we're looking for the area. So the areas of the rectangles are given. We're going to use factoring to find the expression for the missing dimensions. This doesn't always have to be exactly just because, for example, I'll show you why this is a little bit of a weak example. If I had this that said, oh, it's a 12-unit circle, 12-unit squared rectangle, it could be, oh, maybe it's a 2 by 6. But some of you said, but a 3 times a 4 works too. It could be a 12 by a 1. And the answer is all of those are actually true. It could be any of those, okay? So same thing here. Just because I can pull something out of both of those doesn't necessarily mean that is going to be the dimensions. But we're going to use the factoring that we did here. So what would I do? I would do the exact same thing that we did before. So I'm going to pull out what I can, starting with a 7. So 7 goes there, a 2y squared, and 5y. And then I notice that I can pull a y out right there, and a y. So I get 2y minus 5. So there we go. What are my dimensions? Well, the dimension here could be a 7y, and a dimension here could be a 2y minus 5, like that. All right, your turn. Go ahead and try this and see what you come up with. Pause the video and check the answer. And here's what we get. You can factor out an 11xy from both of these. And we're left with an x, just that one there, because that's a squared. A 2, because 22 divided by 11 is 2. And the x goes away because of that one. And one of the y's goes away. We're left with that. All right, you're responsible for finishing up this page here. And I forgot to give you instructions here, is factor out the GCF. So that means all your answers are going to look like this here, where I factor out a 2 here, so we get 4x plus 5, and that's my answer right there. So however you do it, if you are going to break these guys up and then circle them, or do the ladder method, or you just see it and pull it out to get to here. Whatever cranks your tractor, whatever floats your boat. Ready, set, go.